Okay, last subject matter here with energy is power. And to talk about power, we'll need to give it a nice definition of what power is, obviously. And power is how fast we do work. So the rate at which work is done. So define power, average power, work divided by time. Now here's what's important. Remember, work is energy. So it's the energy that we use divided by time. So this could be potential, could be kinetic, could be the energy on a spring. All those things could give us power. All right. So it's the energy transformed over time. If we transform energy, a certain amount of time, we have power. The unit of power is this W. Okay, the W is a watt. A watt is the same as a joule per second, which is energy, right, divided by time. So that's where that comes from. Now, when we talk about cars, you read about horsepower. Horsepower in watts have a conversion. 1 horsepower is 746 watts. And we'll talk about how that conversion works here. But just understand that when you see horsepower, we can apply that to this, and we can apply it to the metric system with watts. So that is something that we need to be able to do. Another equation that's useful, all right, and this is one that textbooks show sometimes. I'm showing it to you here. Power is force times speed. So the power at any given time is the force times the speed. And this is an equation that will make life easier. And again, I'll give you a sample problem where that happens, okay? So that's power. So let's give an example here. We got a semi that's going really slow, and you decide to pass on the road. Now, the question is, does my car have the power to do this, right? What's the minimum power required to do this? So we have the mass of the fancy car. We have its initial velocity. We have its final velocity, okay? And we have the time frame of our pass. And so first thing we want to think about is what power is equal to, right? Power, work over time. We also know that work is the same as change in kinetic energy, work energy theorem, okay, which is the same as kinetic energy final minus kinetic energy initial. So let's do some math here to find what our work's going to be. The final kinetic energy is the mass, so 1,300 kilograms, multiplied by our final velocity. When we read the problem, it's 17.9, all right, squared, minus 1/2 times 1,300 times our initial velocity, 13.4 meters per second, and we want that also squared. We do all that calculations, and we get work to be 91,600 joules. So we have the work needed to do by our engine. Now we take that, and we just substitute it in for here, okay? So we say power is equal to our 91,600 over our time of 3 seconds. And again, the time has to be in seconds. If we have something that works for longer than seconds, the power is going to be a really, really small number, and it might not be negligible. But we need to know that it has to be in seconds. So we take this divided by 3, and you'll get, and I'm going to round this, 3,500 to 0 watts. So again, watts, not something we're used to dealing with. So if we want to convert watts to horsepower, we just divide by 746. And then what will happen is we have our answer in watts. We divide it by 746, and we find out we need 41 horsepower to do that. So cars can do that. But that's how we can find power. And remember, use your work theorems, changing kinetic energy. At some point, either on this video or the next, I'll show you how to use potential energy to do that also. Okay, so now this is another problem that comes up with power. We have a force to keep this car moving with a constant speed, all right, constant speed, up a slope of 5 degrees. The engine delivers 50 horsepower to the drive wheels. What is the maximum speed of the car? So we want to find max speed. So step 1 is obviously we have to take our horsepower and convert it to watts. All right, so if we have horsepower and we want to convert it to watts, we know 1 horsepower is 746 watts. So we just take 50 times 746, and it's 37,300 watts. So we have this first calculation. We know our power in watts. All right. We want to know how fast. This is where this equation is useful. Power equals force times velocity. We know our power is 37,300. We know our force is 1280. We multiply that by v, and we can find our velocity. So quick division. And we find our velocity, the max velocity of our vehicle, to be 29.1 meters per second. So that's where, if you see force in a power problem, instantly go to this equation. Or if you see velocity in a power problem and you want to find things, know that power is force times velocity. Last equation I want to show you is something that might come up. You might see it somewhere. We probably won't see it here, but if we want to find the efficiency, especially of an engine, we take power out compared to power in. So the power's in and the power we get out. Never, ever, ever will this number, okay, be greater than 1. It'll always be less than 1, okay, because we'll never get 100% efficiency out of an engine. There's just too many things going on, frictions there. If you ever can do this, if power in and power out is equal, you've solved energy problems. You'll make the most efficient running vehicles ever. So efficiency, ratio of power out compared to power in, and that might come up somewhere in reading or in something that we do later on. So just something for you to know.